Yes, I'm hearing you.
Okay. If you want to go ahead and get your camera ready.
I thought I got you.
All right, we can see you.
Oh, great.
And whenever you're ready, we're ready for you. As long as your,
Thank you.
microphone's on. Mute your speakers.
I'm using the speakers on my computer as well. Yeah. Right. Um, I'm Dharma Ganesan. About our ongoing work. There's an echo going on here. Sorry. The computer speakers are not muted. You want me to mute that as well?
If you can mute your speakers.
Are you able to hear me?
Dharma, can you hear me?
Okay, great. Sorry for the trouble. And I am Dharma Ganesan. I'll just talk about our ongoing work on the topic automated traceability. It's a joint work with Michael and Jan. Michael is sitting over there, I believe, and Jan is an intern from Germany who helped us implementing the IRSim tool, which I will. So I'll talk about the problem and motivation, and then move on to the brief overview of the tool. Then I'll give an overview of the results, empirical study we performed using the tool. First of all, the problem, main problem, many NASA projects require traceability, and it's tedious to create and maintain traceability because it's large systems, so many requirements, so many components, modules. So it's not so easy to maintain such traceability matrix. As we can see in the picture, we have many artifacts, for example, requirements, test cases, and source code. One thing that's not necessarily clear is how are requirements related to test cases, how are test cases related to source code, and how are requirements related to source code. And even within a particular artifact type, like given a requirement, what are the other similar requirements? Similar could be, dealing with the same concept, for example. And there are similarities among source code files. We will talk about similarities. So in our work, we are interested in traceability between set of artifacts. It could be requirement and source code, requirement and test cases, even bug reports, user manuals, etc. Anything that's a text file is of interest for us. Okay, so why are we trying to retrieve traceability rings? Well, we want to help V&V process. During the V&V process, many times the analysts have to trace from a given requirement to an implementation, check whether implementation really implements the given requirements. That's not an easy thing to do, tracing manually the source code for a given requirement. Some kind of program understanding is also needed, and program understanding often requires understanding where a requirement is implemented. Uh, Even for engineers, the regular engineers for programming and bug fixing and maintaining the code, they often have to do the tracing from test cases to source code, requirements to source code. This is some key motivations for our work. So the idea we are following is to sort of extract or retrieve traceability links through uh, information retrieval technology. We want to be able to have some kind of a database, we call it index, which is based on different artifacts. Like we have requirements, test cases, and source code. We build an index. When I say we build the index, I mean the tool builds the index. Index is like what we see at the back end of a book, some words and the page numbers, something similar. Words and the files, those words appear. Once we have that index, we could apply information retrieval algorithms and produce traceability links as an output. So that's the bigger picture. Okay, I'm going to talk a little bit about the IRSim tool that we are working currently. It's a web application, which is good in the sense we don't have to install anything on our machine, just need a browser, of course. We could upload the archives that we would like to analyze. If uploading to somebody else's server is a problem, then we could also run it locally. IRSim runs on a local machine. User can select the files that they want to index, like exclude files by certain extensions or by directories. Then the tool takes it over from there. And the model of information retrieval we are using is called the vector space model. I'm going to talk about it briefly. And Lucene is the Java implementation that we are using for building the index. Okay, here is a screenshot of as soon as you uploaded a package, the tool will try to figure out all the extensions. You can see HTML, DAT, C, log, doc, log, logef, h, prc, zip, whatever file extensions in the zip file. How many times a particular extension occurs, and the analyst can decide whether he wants to index it or not. So by just clicking on this button, he can activate it or disable it. So sometimes we see weird extensions. Weird for us. Suppose we don't know what that log e file stands for. Just click on the example. The system will show you one particular file. So suppose you have a new programming language and we never used it. Just click on the example. You know what that syntax, what that extension stands for. So it's just a way of exploring in the very beginning phase. And it also provides some useful metrics. How many extensions, how many files for each extension. All right. You can also upload files by directories. You could say, I don't want files under sample app to be analyzed because I know through some other analysis they are not real code, so I would like to disable it. So the user can disable folders even go to the leaf file level and select files he wants to enable or disable. Okay. So one thing the user must also do is selecting the parsing methods. We have a lot of files typically in a project, upload it. How do we parse the file? Should we split the words? Like in programming, people put words together, right? Like camel casing, for example, is a mix of two words. It's a camel and cas and then camel cas. So if we use camel casing as a strategy for splitting, we try to find where the characters are changing from upper to lowercase and we split it there. So this particular word will result in 3 words. And we can also use standard parsing technique, which is basically use a list of English stop words, ignore them, and keep the rest as it is. The user can define what are the stop words you would like to consider. And then there's also another type called simple parsing type, which is basically converting uppercase to smaller case, lowercase. That's all. And we have designed in a way that more parsing methods can be added if needed. We have the Java interface oriented design. We are not really dependent on any particular programming language. So the archive has some Java code, some C code, and some Ada code, Fortran code. It doesn't matter for us because we are not really parsing from a grammar standpoint. We're just parsing it as words. So we treat every source code as just a text file, essentially. Okay, which makes it easier for us to use it on multiple systems or systems with multiple programming languages as well. Okay, let's move on to the IR world a little bit. The key idea of information retrieval, in particular the vector space model, can be traced back to 1960. This is a long time. And Gerard Shelton proposed the idea of modeling documents as matrix. It turned out that even matrix can be used in real world. I studied linear algebra before 25 years in 1990s, and I was not really sure how linear algebra can be useful. I was really surprised when I learned this one, that this is so interesting. And the idea is very simple. Well, it's simple now. You have all the terms in your collection, and you have all the documents, and there is some weight for each term in a particular document. I'll talk about the weight in a moment, but you imagine some kind of importance, how much importance you want to give for a weight for a term to a particular document. So you build this term dot matrix. Well, the tool will help, of course, in building the matrix automatically. So usually this matrix is so huge. When I say so huge, depending on the number of files you upload, it could vary between as simple as just 100 terms to million terms, depending on the programming language complex, the system that you're analyzing. We have seen systems where the matrix size goes into 1 million rows and 1 million columns or something like that. If you keep the level of abstraction at the function level, it's even much more bigger. If you keep it at file level, it's of course smaller because the file has many functions. So the matrix is slightly smaller. Anyway, once the matrix is built, the many interesting questions can be answered. You can answer very simple questions like, given a document D1, what are the other documents that are similar to D1? And the angle, measuring the angle between documents turned out to be the answer for that question. Just as soon as you have a matrix, every column, right, is a vector. And you can also view every row as a vector. And once the vectors are there, we apply vector algebra to answer the questions. related to traceability. For example, here is the weight options for the matrix that I talked about that are implemented currently in the tool. A simple option is Boolean option. If a term is present in a document, put 1, otherwise put 0. Then there's a term frequency, which is counting how many times a particular term occurs in a particular document. The analogy or the intuition here is the more times a particular term occurs in a document, the more importance it carries. That's what the idea of TF. But then the TF IDEF is very close to TF idea. However, it tries to suppress words that are occurring frequently in all the places, in all the document collections. For example, if you have a source code from NASA, source code package from NASA, the copyright may have word NASA, and the word NASA could be present in almost all the files. And NASA is not an important word because we know that it's present in all the places. So the TF IDEF idea is to suppress the importance of words that are present frequently in all the places. So it automatically takes care of that. IDEF stands for the inverse logarithmic function to reduce the importance. All right, here's a visual representation. We have once you have the matrix, we could view it in this way or this way. The left way is treating the terms as axes and treating the documents as vectors. And the query is also a vector. If the user says, I'm interested in files similar to doc3 or doc2, that's a query. And that query will be basically comparing with the rest of the documents. So how do we interpret the angle? If two vectors are nearly orthogonal, or in math terms 90 degrees, then we are thinking that they must be dissimilar because there's nothing common. If the two vectors angle is towards 0, which means they are pointing in the same direction. Okay, which means there are a lot of commonality between the two vectors or two documents, if the vectors are document vectors. User could define the threshold saying that, what I'm interested in document pairs whose cos angle is more than 0.8, cos theta value is more than 0.8, then the tool will filter out other pairs which violate those threshold definition. Okay, so here is a little formula. We don't have to go into the details. If this is a Boolean matrix, right? You only see 1 and 0, and we can easily compare document D1 and document D4, and we can see from our intuition D1 and D4 are similar because terms D1, D3 are present in both places, right? Only T4 is present in D4. So the cos theta is 0.8164, which is close to 1 in the sense they are pointing in the same direction. Okay, so that's the underlying algorithm we have implemented, and the tool will basically show a matrix, not exactly like a matrix we typically see in a Word document. We see a table basically, and the first column shows the score. Score is a similarity score in this case. This column shows the requirement. We have every requirement is stored in a separate file because the vector space model requires that. And if the requirements are in an Excel sheet, we can take each requirement and put it into a file. The tool allows how to parse a CSV file, how to take out individual requirement. That's kind of automated now. And the user can also define patterns for how to chop the text into pieces. So the second column shows how similar the first document is to the second document, and tokens is just counting the number of words. We would like to know sometimes we see score is 1 and then we are surprised, oh, we found a duplicate file. but then the number of tokens may be so small, like a very small exception file or something like that. So the number of tokens is a way to sort of filter out during the analysis and sort of not interesting areas. All right, that is what the main feature of this particular tool. For the empirical study, we asked two questions. What is the best weight formula we should use for the term doc matrix? Because there are three types of weights like TF, IDF, and Boolean. We don't know which one will produce the best result. And then there's also another thing, text parsing. I explained three types of text parsing: simple, standard analyzer, and camel casing. So which is the best strategy? I mean, these questions are difficult to answer in general, because it could be that for one system, one particular type is better, but we are trying to do some experiments to get feel for it. Okay, so we are going to use the NASA's core flight software as a case study to evaluate this software. When I say this software, I mean the IRSim software. So a little bit overview of flight software. It's a flight software used in many NASA missions. It's a product line, and it's written in C, and there is an OS abstraction layer as well. We have studied those architecture for several years, so we have a good understanding of CFS in general. Here are some metrics about the requirements. We focused on the core flight executives layer of the architecture, and we selected these 4 modules for the empirical study. As we can see here, we are dealing with 272 requirements, and each requirement has a requirement ID, requirement text, and some rationale. We wanted to take this requirement document and trace each requirement to the source code. That's the goal of the study. Okay, here is an overview of the source code in terms of the metrics. The execution service has 2,500 lines, software bus has 589 lines, time service and table service has 1,000 lines. Overall 5,000 lines we are dealing with here. Okay. The golden model is something we prepared to evaluate our IRSim tool. So it's a manually prepared model. We did a manual tracing from each requirement to the source code, including header files, C files, build files, and configuration files. And we wanted to see how much IRSim is close to our golden model. Sort of, we wanted to have some view of precision. And we also validated the golden model because of our previous experience in analyzing the source code. Okay, so what is there in the golden model? The golden model has ID, requirement, of course, and then the file which we think is implementing this particular requirement, and then the name of the function. This is manually built Excel sheet based on manually tracing each requirement to the code. Okay. So what is the evaluation procedure? We wanted to look at the top 5 results of IRSim. We want to see how many of the golden model elements are present in the top 5 results. We have chosen top 5 because we are kind of strict, right? Top 10 means we allow more options. Top 5 is very strict on one hand. On the other hand, through our experience, we learned that most of the core logic is implemented in at most 5 functions for a given requirement. So 5 seems to be a reasonably a good number. If you say look at top 10, that means we are giving more freedom. There could be more false positives in it. So we wanted to see how good our algorithm can come into the top 5 results. Okay, we are just comparing whether the expectations of the golden model are present in the top 5 results. Otherwise, we treat as failure. Okay, so there is some metric here. We measure precision as a ratio between how many requirements we traced successfully using the golden model to that of the IRSim tool, and we calculate that as the precision. So it turned out that camel case analyzer. So what you see here in this chart has different modules. I talked about 4 modules in the beginning: software bus, executive service, time service, and table service. And I also talked about different weight formulas, right? The TF, IDEF, TF, and Boolean. So we can see that in all these modules, consistently, TF, IDEF provides good results, right? It has 85. I mean, it's low, but it's 60. It's low, but still better than the other weight formulas, 74 and 87. So we think that based on what, I mean, of course, based on this particular study, the camel case analyzer seemed to perform well for at least 4 different modules that we studied so far. What about standard analyzer? Well, the standard analyzer didn't perform so well, and slightly better than the next one that I'm going to show you, the simple analyzer. So in all the 3 types of analyzers, the recurring pattern is that TF IDEF together with camel casing produces better results than the other configurations that we tried. It's not a, I mean, it is an interesting finding, but on the other hand, the camel casing, if you look at it, we are also partitioning the pieces, right? Because the words are put together, so we are trying to increase the probability of hit. So it makes sense that camel casing comes up as a better candidate than the rest of the parsing techniques. The TF IDEF is very tricky. What we are trying to say is that we wanted to give importance to the words that are present frequently, but not across all the collections. And the TF alone is measuring how frequent a particular term occurs within a document collection. So it's unclear whether TF IDEF is better than TF or vice versa before we did the study. And now it is getting indication that TF IDEF is probably better than TF as the weight formula for the term doc matrix. Of course, we cannot overgeneralize. This is a very limited study, and we have to repeat on other systems to get a broader conclusion, to draw a broader conclusion. Okay. So there's a natural question why IRSim is not tracing all requirements. Sometimes there are typos in the requirement documentation. For example, the word software bus, I'm just making up an example. It's not exactly that particular problem, but we have seen typos like message could be, instead of ME, it could be MA, so it could become massage. And the source code, it could be MSG. So the connection between MSG, message, and massage, tricky to establish automatically. So typos in requirement or in source code makes it difficult to hit. And that is one reason. Another reason we found is that chopping of sub requirements. So what that really means is that the requirements are not listed one after another, right? There's some main text there, and then sub bullets or subdivisions like 1.2.3 and then 1.2.3.1. So how do you know where to automatically chop, into a meaningful piece? That's a tricky thing. We went by the ID of the requirement, but they are not standalone. So having that kind of context information in the beginning will most likely help, because otherwise the requirements are incomplete from chopping standpoint. So that's one more thing we probably have to think about how to improve. And then the source code has a heavy use of acronyms. Like software bus is called SB, and everything is shortened in the source code as much as possible. But the requirement is mostly natural language English, so it's a little bit tricky to automatically sort of recognize the equivalence of English text and its corresponding acronym. So, so we think some kind of wording issues contributed to this slightly lower result. Meaning, for example, we go back to the camel caching analyzer. In some cases, for example, in the executive service, we only got 60% precision. So overall, precision is not close to 95, not at all close to 95. We would like to have something close to 95 at least. It's a difficult problem, of course, to automatically connect the requirements with source code because there are different levels of details and abstraction, right? But this is basically just a regular search, like somewhat similar to grep, but taking all the documents, all the requirements into consideration and search across all the document collections. That's the slight difference between grep idea and this one. Okay. So the summary is that IRSim seem to have the potential to generate traceability links. It depends on the wording of the requirement. If it is a very high level requirement, probably not so easy to trace. With acronyms and so on, makes it slightly difficult. From an empirical study standpoint, combination of camel caching and TF-IDF seem to be the best one so far. And one good thing is that IRSim is completely independent of any programming language, and we treat the C code and the C++ code, Java code as regular text. So as soon as we have Fortran code, we could just run through it. It's not a problem. And to generalize the findings that I discussed, we need to replicate on other systems as well. So essentially need a lot of further validation. This is a preliminary study. With that, I'm actually done, and I would like to thank the NASA team, CFS CFE team. We have had several meetings, not exactly on this finding, but on the architecture and the source code. So their help is appreciated, and we had several interns implementing the IRSim over years, and I would like to thank all of them as well. So with that, I'm done, and sorry for the initial trouble with the voice speaker settings. Created some problems for me, and thank you.
Correctness, completeness, etc.
Those are very interesting questions, and thanks for the comments as well. The IRSim is an implementation, web implementation of the information retrieval algorithm I mentioned, vector space model. So we are implementing a web-based tool basically. An analyst can upload an archive. It could be a zip file or a WAR file, some kind of archive, and he works without installing any tool locally on his machine. And so we are trying to develop the tool for that as well. And there is a prototype version which was used for this particular study. And second question is that once we generate the traceability links from requirements to source code or requirements to test cases, we can't automatically validate, right? And the scope of this experiment is to check whether the tool suggestion makes any sense. That's why we build this golden model, sort of a model what a human would produce, and an expert in this case will produce, and we use that as a basis for comparison to see whether IRSim suggests anything meaningful. We are talking about correctness of the suggestions given by the tool. What we don't know is how complete the suggestion is, and those kind of things are trickier to automatically suggest from the tool. I don't know whether I answered your questions.
'24, please. We just kind of stepped through that one quick. I just wanted to take a look what you were doing with the requirements there.
Oh,
You
sure.
had some kind of precision going on, but we kind of stepped through it quickly.
So we wanted to figure out how many requirements we are tracing. Say, let's assume we are tracing 4 requirements, and how many of them are present in the top 5 in the source code. And if we get 3 of the hits in the top 5 results, we consider we got 75% precision. So we are measuring how much of the requirements that we expect to be covered are covered by the IRSim tool. No, we are not really doing that. We are taking all the requirements. So let's assume we are tracing 4 requirements. So that's why the denominator is 4. We are counting how many of the expected functions of the golden model are present in the IRSim's top 5.
Elements are fulfilled.
That's right.
Got it. Thank you.
Sure, sure. I was moving through slides locally on my PowerPoint, and I realized that there was a PowerPoint on the Adobe Connect, so I was not moving the slide. Okay, great.
Okay, Dharma, I have a couple of one comment and a question.
Sure.
On slide 15, I noticed that all the files you looked at had TXT extension. My comment is that my question is, in real life, in real production, I don't get the requirements in text. I mean, in a text file. You get them in PDF files. You get them in drawings. A lot of them have diagrams and images in them, and so somehow you have to be able to have. So it looked like your tool requires that you have to have been able to somehow taking the files, taking the non-regular text documents and transform them into text documents. Is that correct?
It's a tricky problem what you're talking about. I fully agree that nobody gives a requirement in a separate file. That's why we try to have a parsing methodology, and there is a way to parse files based on a pattern. So if all of your requirements are in text, if you could bring it to a text file, CSV file, for example, Excel sheet, then we could parse based on the requirement ID. If it is an image, unfortunately, that would be too difficult. We don't have a way to check requirements from the image. I mean, maybe some advanced image recognition technology would help, but that's not yet implemented.
Thank you. Now, my comment, is that from a software engineering perspective, I think one of the things you teach your team, or that you try to implement in your software development process, is that you encourage your engineers to do their traceability, enter the traceability information as they go forward, instead of having to do it automatically at the end. The idea is that it puts the onus on the engineer and the developer, on the engineers in general, the developers and the test engineers, to do their traceability documentation. Now, this tool turns all of them into lazy people. It makes them not do it takes the work away, it makes them not do the work. Just a comment. Okay.
The viewpoint we have on the tool is that it's slightly different. We have somebody manually develop the traceability matrix. Can we really validate that? So we want also use the tool for validating existing traceability matrices. And if there are cases where there are no traceability matrices, then we wanted to be able to, get one. And the traceability matrices that we usually see are at a higher level of details, or a higher level of abstraction, I must say. And here we go even to the function and file function level details. So there is a slight difference in the level of details that we could go through.
I hope you.
So thank you very much.
Thank you very much
your
for organizing
presentation.
this. Thank you.
Thank you very much for organizing. Thank you.
Okay, everybody, we are done today. We will be back here tomorrow morning at 8 a.m.